Testing, testing. All right. So this talk is about, obviously, EVP and VXLAN, but even more than that, it's about things that you can do with it and ways that especially service providers and network operators should think about how they can make use of this. So, absurdly basic recap of networking. Historically, in layer 2 networking, we had a very clearly defined LAN and WAN, right? LANs were these very cheap, small networks that connected a handful of local devices. And there's obviously major known issues with scaling that out. So you had very small sized LANs. And then whenever you wanted to connect multiples of those together, whenever you did them over distance, whenever you did pretty much anything, you had a very clearly defined WAN. And these circuits landed on big expensive routers, and they were used to aggregate and route and do all of this stuff. The actual technology behind the individual circuits is less important. It's more of the architecture, what you built with it and what you did with it. And when you built the overall network, you needed some type of more scalable technology than a traditional LAN network. And the reason for that, today, everything that we do is based on Ethernet, right? This was originally a LAN protocol, but purely by simplicity, low cost, and just massive market penetration, we've seen Ethernet completely displace every other form of technology out there. Even the things that were technically superior, we use Ethernet for almost everything, and Ethernet-based things wherever possible. But the reality is we're still struggling with the origins of Ethernet being what it was. It wasn't designed to ever do more than some of these very small LAN networks. So we keep adding protocol extensions, we keep adding things to try and make it more scalable. But historically, that's where Ethernet came from. That was the role. And the reality is, compared to any kind of layer 3 technology, Ethernet, in terms of scalability, just sucks. I mean, it is terrible. There's all kinds of ways to completely destroy yourself. Loop prevention is absolutely critically important to every single thing that you do. If you don't have a way to prevent that, then there's no TTL. There's no way to deal with this in a graceful fashion. If you have any kind of a loop whatsoever, you're done. You're wiped off your entire network, and you've probably wiped off a whole bunch of nearby things on connected devices. You have very limited, even with VLAN technology, you have very limited scale. You've only got 10 bits to work with in VLAN scale. So 4,095 VLANs really doesn't go very far when you're talking about building any kind of large-scale network. And if you were to build something in a pure native Ethernet, you would have to update every device in the transit path. So if you had 5 routers and connecting point A to point Z, you have to touch every single thing in the middle. Provision of VLAN, there used to be all kinds of hideous protocols that would do this, that would signal between the devices, and it caused nothing but problems. And any kind of mechanism to do redundancy in a pure native Ethernet, pure layer 2 environment is just terrible. I mean, there's no good mechanism whatsoever for this. So every single thing that we build in a modern network is constrained to a very simple environment, a very simple role. It's a point-to-point, or it's a small LAN, even though we're still using Ethernet technology. And of course, we reserve a special place in hell for anyone who violates these rules, because it usually results in something very, very bad happening in life. So how do we use Ethernet to do large-scale networks? Well, there's 2 main methods if you really break it down. One is we can cheat and just use a dedicated layer 1 service. So for example, if you get a dedicated 100 gig wave and you run 100 gig Ethernet across it, you're not really running much of Ethernet, you're getting it as a wave. Or maybe you're getting a 10 gig wave, which is really just an OTN segment on a 100 gig wave, but it's cheating. It's a layer 1 service. You're not really getting into any kind of complex layer 2. The other method that we use is we emulate Ethernet on top of some other technology. So be that L2TP, layer 2 tunneling protocol over IP, or be that MPLS with things like Draft Martini, VPWS, VPLS. There are all kinds of technologies to take this more scalable network and then emulate some kind of simple Ethernet service across it. MAC and MAC transport, provider backbone bridging, comes into popularity every so often. But between these types of things, this covers almost every method that people use to deliver some kind of scalable transport Ethernet service. This works pretty well for kind of simple circuit emulation stuff. So a very common thing that you see is a carrier selling a virtual Ethernet circuit across their MPLS network. right? They have a converged IPL MPLS network, and while they have it, they can say, oh, here's a 50 meg circuit, here's a 1 gig circuit across my backbone, and it all rides the same infrastructure. But if you start to look at the world of cloud services, even this type of technology really starts to hit these big fundamental scaling limitations. If the button works. So what do I mean when I say a cloud environment? So let's think for a minute about what happens inside of the world of a hyperscale cloud provider. You've got tens of thousands of servers. You've got these servers that are connected in distinct pods. And you're virtualizing the workload. You're distributing it across a large number of servers in a way that the workload will change constantly. You can move, you can shift. You're getting a lot more efficiency. You're able to pack many different workloads, and you're able to not have a lot of infrastructure, CPU that you invested in sit idle while other is sitting full. You're able to really control and scale your workloads in a much more intelligent fashion. And as you scale horizontally with servers and pods and things like that, you also start to scale in terms of the applications, the individual things that are trying to work with each other. And the point here is you have no real guarantee as to what device is going to be talking to what device. In fact, you pretty much know that you're going to be talking to a very large number of devices across this very large set. So if you imagine that there's tens of thousands of servers and you've got an application that needs to arbitrarily talk to 5 of them, this is something that traditional Ethernet services are not meant to do, but it's something that's expected in the world of building cloud infrastructure. So what did cloud operators do? They started building these fabrics. This is from a Facebook presentation from 2015, kind of talking about a spine leaf architecture, but it gives you an idea of kind of what these things look like. They start to build these fabrics that actually look very much like the construction of a fabric inside of a switch, right? What you're building is a very simple, very cheap, dumb connectivity, dumb pipe, and any point-to-any-point connectivity. But like I said, when you've got all these applications, you've got hundreds of thousands of services out there being spread across tens of thousands of servers. Well, how do you configure that? How do you control that? What's the mechanism for it? That's where you start to get into some really unique challenges. So one notable early attempt to improve this was something called VXLAN, which stands for Virtual Extensible LAN. So the simplest, most basic description of this is taking these layer 2 frames and tunneling them inside of a UDP packet and routing them across IP. So you see in this scenario, you've got a VM on the left side and a VM on the right side. What's happening is you're going to an upstream switch. It has a virtual tunnel endpoint, a VTEP. And it says, oh, I need to get from this device to that device. It's going to take your layer 2 frame. It's going to take this MAC address here and all of the data. It's going to slap it inside a UDP packet, ship it across an IP network that knows nothing about the underlying services, hand it off to the other end. And so what you actually got was, from a core network perspective, the only thing you had to do was carry these loopbacks. So it's very simple, very scalable. You can build these very massive topologies out of it. But why do this? Well, remember what we said earlier about how you scale a layer 2 service. Really, the most scalable, reliable things that we have out there aren't running more complex layer 2 networks themselves. They're emulating layer 2 services across something that's a little more scalable. So VXLAN really takes this philosophy and kind of takes it to the next level. So it actually says that you should have a very distinct underlay and an overlay network. You should have a piece of your network that is completely dedicated to being nothing but a simple core, and you should have a piece of your network that does the services on top of that. So for the underlay, the goal here is to use the simplest, cheapest, most scalable, and most pervasive thing that you can possibly find. Well, what is that except IP, right? That's something that we've built massive scale. We've built the internet on. We know exactly how it works. We know exactly how to scale it. It doesn't need any new complicated technologies. It doesn't need much of anything. And we know how to make these very, very massive, scalable, cheap IP networks. The overlay, what you're looking for is to use the underlay as the transport mechanism. And the overlay is about the services. It's about connecting the endpoints together. And what you want is something that's really simple, lightweight, low state. So you kind of get that by taking these layer 2 frames, putting them in a UDP packet and shipping them. You really didn't have to do much in the way of state, especially compared to every other technique out there. So the original motivations behind this were, like I said, kind of all about cloud, right? When you're trying to build these massive scale cloud infrastructures, you have to have a way to solve these problems. So VXLAN took you from a 10-bit field in VLAN space all the way up to a 24-bit field. So you get 16.7 million possible combinations. That's enough to work with. It's very easy to do VLAN mobility, right? You can move these VLANs around across this very large network. You get your multipath forwarding taken care of through the ECMP properties, the equal cost multipath properties of the underlying IP network. So it's just kind of, it solves a lot of these complexities by using this very standard, very proven technology. And like I said, it really removes a lot of the state necessary. It makes it so that, in the core, obviously, there's no state whatsoever about the end services. All you're doing is connecting loopbacks. But even on the edge, if you look at MPLS type services, you're still, for example, using LDP to signal every individual service. In this case, you don't need to do that. It's very, very lightweight in state. It lets you scale very much. But VXLAN is not without its own set of disadvantages. So really the problem here is because this was designed for cloud, it was designed for kind of known friendly traffic. When you're the one running the servers and you know what they're all sending and you control it, and assuming that you've not been hacked, you have a pretty good idea of what that traffic is, and you know that it's not going to be malicious or weird. So VXLAN really lacks any kind of signaling protocols. There's not like a protocol where these things, the individual routers talk to each other and signal. It doesn't have that. What it expects is to be configured by SDN. And by SDN, I mean there's some kind of an orchestration layer that goes out and talks to the individual devices that tells it what instances should be out there. So because of this, it's really not scalable for applications outside of kind of these very basic cloud infrastructures. It also uses a really simplistic flood and learn data plane driven mechanism for learning its forwarding. So just like Ethernet, when you get a frame and you have no idea where it goes, you broadcast it everywhere and you hope that whoever you sent it to replies, and then you listen to that reply and hope that you now know where it goes. That's not a very scalable way to do that. In fact, that's one of the major inherent problems with scaling an Ethernet network as it is. So that kind of creates a real problem in taking this and kind of building it out to massive scale. And you can incur some significant overhead in that too. The broadcast broadcast unknown unicast and multicast flooding. You can incur some significant overhead in this trying to figure this out, even assuming that you are able to figure everything out perfectly, correctly. It creates real problems. The other major problem with VXLAN is it assumes that you will have a multicast enabled underlay to handle that bum traffic. That's a pretty serious problem for any kind of a brownfield network, anyone who's taking an existing deployment and trying to roll this out, or pretty much anyone who doesn't trust multicast. And where I come from, that should be everyone. So there's a way to solve that. Enter another protocol, EVPN. So, oh great, another protocol. What does this do? So EVPN stands for Ethernet VPN. Think of it as an evolution on some of the existing L2 VPN type technologies that we've had with things like VPLS. Effectively, what it's doing is it's the advanced control plane that VXLAN doesn't have. So what does EVPN do that's different? Well, it turns this from a flood and learn data plane driven mechanism to a signaling based protocol. So effectively what you're doing is you're routing MAC addresses through BGP. And Marty Hannigan, if he's here, nobody punch him. This is a very scalable, this is a known scalable way to route millions of routes through infrastructure that already exists. We know how to have BGP speakers. We know how to have BGP speakers talk to thousands of endpoints. We know how to have them pass millions of routes. It's a known scalable way to do this. It really helps you do things like rapid MAC moves. So it lets you really do your VM mobility stuff without kind of hairpins of traffic. It eliminates the need for the multicast underlay, so that solves a big problem for a lot of people. And it natively supports something called layer 3 gateway functionality. I'll talk more about this later, but this is a way for a layer 3 service to utilize the EVPN service. So really, think of EVPN and VXLAN as the chocolate and peanut butter of Ethernet emulation, right? This is the perfect combination. It was the marriage meant to be, and they really solve a lot of problems for each other. So the EVPN piece solves the reliable, scalable control plane. It's how you it's how you have large numbers of POPs, large numbers of devices, large numbers of service instances, and make this stuff scale. VXLAN is how you do the data plane. It's how you have a very simple, very lightweight, very low state mechanism that can do massive amounts of traffic cheaply. And this is something that's already seen widespread adoption by pretty much every major ASIC manufacturer that's out there. So the end result is you get the best of both worlds. You get all of this highly scalable from a service perspective. You get highly scalable from a bandwidth perspective. And you don't lock yourself into vendor limiting things. I mean, one of the big problems with MPLS, to be honest, is most people kind of know if you want it done right, you kind of have to go to Cisco or Juniper. Well, why? Because they wrote the thing. They're the only people who really know how to do it well, and it locks you in. It locks you into some vendors where you might not have other choices. You might not be able to bring in people like Arista. You might not be able to go out and easily create your own stack on white box hardware. So not being locked into a pure MPLS network is very compelling. It adds some serious economic advantages. So what if you're not building a cloud, right? What if you're just an NSP trying to build a network? What does this do for you? Well, just because this came from data center networking and infrastructure doesn't mean that it's not applicable in a lot of other areas or across a WAN. So if you think about the way that we built networks historically, and kind of compare it to the way that cloud versus bare metal works. Historically, we've used a very bare metal approach, right? We've bought a specific device of a specific size, specific capacity, and we've tried to make sure that the right size box, because you don't want to overbuy. You don't want to put in a giant router where you don't need it. You don't want to put in a router that's too small. So you're out there constantly changing, shifting, upgrading to make sure you have the right box in the right place. And you pretty much need this everywhere. You need these full table, full functionality routers deployed at every single location of your network. So if you were running an NSP, historically that's what that meant. You know, if you were an ISP, every one of your devices was expected to have a full table, was expected to know all about the internet, make its own routing decisions. And you had to go deploy these everywhere that you wanted to have service. So if you had, for example, 10 POPs in a metro, you probably had 20 devices. You probably had a pair in each one of these things, and these were all full functionality devices. And as capacity was needed, you would have to scale them up. So you spend a lot of time maintaining that network and a lot of cost that goes into that. One of the early generation attempts to optimize around this was what's called the label switching only core. So this was an MPLS-based system where in the core, you wouldn't need a full FIB device. You wouldn't need to carry a full internet table. All you would do is label switch. So you could, for example, optimize for a different device. But one of the big problems here was you still needed some carrier-grade MPLS speaking thing. And the vendors didn't really have a great motivation to create this particular product because they wanted you to keep buying their big expensive box. So there were many, many, many years where they talked about this and didn't actually deliver it in any kind of scalable way. And even though you're starting to see some of that now, it's still not nearly as good as a simple IP core, right? You can get some very good economics on a simple IP core and have a complete selection of vendor choice that you don't get when you work with MPLS. So what if we change that model, right? What if we could do for networking what cloud has done for compute? So the mechanism here is, just like we talked about earlier, you start with this fabric, this very simple network that all it does is very scalable, very cheap, dumb connectivity between large numbers of endpoints. You can use very optimized hardware. You don't need large FIBs. You don't need MPLS features. You've really got the world is your oyster as far as what you want to pick. And there's a lot of great functionality out there that's been built for support of these cloud infrastructures that a lot of people don't realize that when one Google data center talks to another Google data center, that can do more traffic than an entire tier 1 does to the entire internet. Right? The implementation of cloud services is one of the largest consumers of bandwidth by far. The cloud guys are the ones who are consuming 100 gig transceivers by the boatload. They're the ones who are really consuming this stuff in great scale. And in doing so, there's a lot of economy of scale that you get out of these technologies that you historically didn't get in the NSP world. So now when you want to build a service on top of that, now you virtually connect all of your high-touch devices using this common fabric. So let's say that you have routers that speak BGP, that do peering, that do all this stuff. Now you only need these where you need them. So in that earlier example where I said there's 10 POPs in a metro, you don't need 20 full table devices. Maybe you only need 2 or 3 or 4. Some number for redundancy, some number for locality. You want it spread out for survivability. You want more than one, obviously. But you probably don't need 20. So it changes what you need. And like I said, it's kind of similar in concept to how a switch fabric works inside of a router. You start with a fabric that is very simple, very cheap, very scalable bandwidth, and it's all about that dumb connectivity. So EVPN VXLAN really provides the technology that you as an end user, someone who's not out creating your own protocols or creating your own ASICs, it really provides you the techniques that you need to do this well. So for traditional carrier networks as well as data centers and clouds, it's something that you can go out, configure today, and have it work. And this model scales, and it supports millions of virtual circuits, hundreds of thousands of devices, and hundreds of terabits per second of capacity. This is something that's out there that's happening very cost effectively. So when I mentioned earlier about the EVPN layer 3 gateway functionality, basically what's happening here is it's a way that you can have a higher level service. It's a way that you can have a router service join an EVPN instance. So you might have a pair of routers that sit in some centralized location. So instead of going and putting all of these out in all of these POPs, they just join the instance that they want. So when a customer says, oh, I want BGP, well, now you have a device that says, oh, okay, I'm going to connect to this customer's instance on ID 12345, whatever that ID is. This is something that's very scalable programmatically. It's something that it makes maintenance easier. It makes all kinds of stuff easier, where you can start to attach multiple devices for redundancy. You can take a device out, put a new device in. You can map and move this around for traffic. It really changes the way that you go deploy your more advanced services, your routing, your firewalls, things like that, in a way that is much more efficient than kind of that traditional bare metal approach. And you don't need these big expensive routers in every part of the forwarding path. And like I said, you can consolidate and aggregate, right? So instead of, you probably have pick a size of your network, right? You probably have some box that is meant for a large amount of capacity. If you go look at what is your actual traffic, what is your actual packets per second through that box, it's probably not very efficient. You probably don't want to run your routers all the way up to their maximum, because then you're very close to having a little bit of traffic push it over the edge. So in doing this, you get to make more efficient utilization of the resources that you have. You get to kind of pack it a little bit better and make it easier to very rapidly go out and install another device. It changes the economics in a way that is very compelling for providing these kinds of traditional NSP services. So what does all this mean from a carrier economic model? Well, if you look at kind of the big expensive routers that are out there, and it doesn't really matter who your vendor is, these are all kind of standard industry prices. It's pretty typical to see a price difference of about 25 to 50x between a fully functional, high-featured, massive native BGP speaking device, modular full router, and whatever your simple, cheap data center networking design device is that doesn't necessarily need to have those functionalities. The commodity merchant silicon that's out there really is supporting this stuff at massive scale. You have individual chips, you have system-on-chip designs that are supporting terabits of traffic very cheaply. You're getting down into hundreds of dollars for these very high-speed interfaces. And historically, it made sense to do it the way that we did it, right? We had to have these routers that were out there. They had to have full fibs. They had to do this stuff. But now that we have a technology that kind of lets us separate the pure fabric connectivity layer from the services that you then provide on top of it, it really makes this more cost effective. So even if you never eliminate the need to have big expensive routers, you probably don't need as many of them, and you probably get more efficient utilization of them. So this lets you scale up your network in a much more compelling, much more cost-effective way. Like I said, similar to how CPU kind of gets crammed together in a cloud environment. And if all you're providing is pure transport, well, then this becomes a much cheaper, much more scalable service as well. So I have some slides talking about kind of EVPN VXLAN itself. There's a couple other presentations that are out there. There's some great white papers that are out there. I meant to add a few more to these things, but I didn't get a chance, sorry. But this is something that has kind of been out in the industry for it's been a couple years now that it's been written and deployed, and it's kind of gone through its buggy phases, and it's kind of hit a point where it's now mature. There's a lot of people that are out there running these services across it, and I expect to see a lot more people kind of migrating to this type of topology in the future. And with that, I have time for questions. Lots of time for questions. Anybody?
Hi, Chris Whitfield. Sorry. Sorry, which one?
Chris.
Okay, I'm sorry. Hi, Chris Whitfield with Salesforce. It's well understood that EVPN does a lot to minimize the bum problem by pushing out MAC table information, ARP information, et cetera. But it doesn't, as far as I know, it doesn't eliminate it entirely. Have you seen workloads that are particularly unsuitable for VXLAN period due to the amount of bum traffic that still gets thrown around?
Well, I think it depends on what you're actually trying to do with it. If you're trying to be an NSP that's out providing service, or if you're trying to run a cloud, or you're trying to do something in between. One of the things that I've seen is there's times when you've got some service that just has a massive number of MAC addresses, that just has a massive, if all you want is a simple point-to-point service, this isn't right for you because you're now participating in the MAC learning and flooding. There's a protocol called EVPN VPWS, which takes the protocol and just makes a simple point-to-point, no state, no learning mechanism. That's something that's in development that a lot of vendors are working on. Kind of the way that I approached it was not entirely reliant on EVP and VXLAN to still have other technologies if needed. But I think more and more you're going to see people moving to kind of a converged, being able to do everything with this one protocol. And like, that would be an example of where if you had someone with tens of thousands of MAC addresses and it was point-to-point circuit, you wouldn't need to participate in that kind of thing at all.
Okay, thanks.
So my question is kind of more trying to understand more of the technology. So the EVPN, is going to share learn the state of the MAC of the layer 2 state, right? So that is taken care by EVPN, or is that VXLAN?
So VXLAN is encapsulating the packet and forwarding it. EVPN is learning the MAC addresses and signaling them over BGP.
Okay.
So basically you have an extension to BGP where you're literally putting a MAC address in as a route advertisement. There's all kinds of extra, I didn't get into the details on how this works. There's been plenty of other presentations that go into every little message type in detail. But that's basically what's happening. You're using this to, and there's mechanisms where you can use this to advertise kind of an anycast thing. There's one of the great things that EVPN adds is kind of native support for all active. And kind of being able to do load balancing across all this in ways that a lot of other mechanisms aren't, or is very, very complicated to set up. Like if you've ever tried to set up redundancy and all active load balancing with a VPLS solution facing a client, it's hideously complex. EVPN really simplifies a lot of that, and it uses all these different message types to accomplish that. It has mechanisms to kind of prevent forwarding loops. It has all of that built in, but it's really the signaling protocol part. VXLAN is really just the data plane. It's the encapsulation of the packet.
Okay, so in the underlay, right? So we're talking underlay, overlay. Is this state being transmitted? Like, can you see it on the underlay? Are my routers aware of that?
On the underlay, no. On the underlay, basically you have, at your simplest, all you need to know is a loopback address. Okay. So if you got a 32 per device that's out there, and this scales to whatever the size of your fib is, but this will scale to a lot of devices. The overlay is taking that and using it, so that endpoint, that VTAP, is being used to do the tunnel encapsulation, but the overlay is what's doing all of the everything else.
Thanks.
Yeah. Any other questions? Well, thank you very much.